You might recall from my networks introduction, a network is a type of graph that's used to show the relationship between things and how they are connected. When looking at a network, it might not always be clear how many paths there are between things that we refer to as nodes. In this video, I'll show you how to find the number of paths between them. Specifically in this video, we'll look at what the number of paths in a network means, the number of paths with no restrictions, the number of paths with restrictions, and the number of paths when you must visit a node. Have you ever gone somewhere and wondered which path you might take? When you go somewhere regularly, like school or work, you might try to take a different path each day to keep things interesting. Remember, a path in a network is a connected sequence of edges or arcs showing a route that starts at one node and ends at another. Here we have a network of streets between home and work. One way to determine the number of paths is to trace them through the network and list them out. The path is highlighted in red in these network diagrams. It's important to note that we won't backtrack. So when we trace the number of paths through, I'm highlighting them in red, and we trace the number of different paths. By tracing these paths, we can see that there are 8 possible paths from home to work without backtracking. Networks may have many paths from one node to another, and it might not always be practical to trace the number of paths in this way. In this case, we're going to use an algorithm to find the number of paths in more complex networks. For larger complex networks, it can become difficult to trace and list out all of the possible paths. In this case, we need something that will help us determine the number of paths. For that, we use an algorithm to find the number of paths through a network from start node to finish node. We work from the start node in the direction of the finish node, label each node with the number of paths from the start node to that particular node. We write a 0 in the starting node. Again, remember that we're not going to backtrack. Then we look to the next nodes to determine how many nodes connect to it. These are to the right and below the starting node. In our example here, we add the number of paths from the previous node, which leads to that node, which is 1. You repeat this process until we get to the finish node. The value at the finish node is the total number of paths. So if we move across and down our network here, across the top, there's only one possible path, so we write 1 in the top. In the middle node, we've got a path from above and a path from the left, so we write 2, we add them together. On the bottom left, we have 1 possible path, so we write a 1. Now on the right in the middle, we have 1 path from the top and 2 from the left, so we add them together and we get 3. In the bottom middle, we have 2 from the top and 1 from the left. We add them together and we get 3 possible paths to that node. In the finish node, we have 3 from the top, 3 from the left, and we add them together and we get 6 possible paths to the finish node. So there's 6 paths in this network. Imagine we worked in the city and we wanted to find out the number of paths we could take from home to work across town without backtracking. We will follow the main roads because they'll generally be the fastest route. We label all the intersections as our nodes, and we draw in all the possible paths as our edges or arcs in this case. Now we can extract the network diagram and determine the number of paths between work and home. Here we have extracted the network diagram from our map and we'll work out the number of paths from home to work without any restrictions. In this case, the arrows indicate the direction. Put simply, we write the number of paths up to each node in each node. We start with the home, we write a 0 in the home node, then we look to the next step in the journey. From the home node, there's 2 possible nodes we can move to. There's 1 possible path to each, so we write a 1 in each of them. There is only 1 path across the top and down the left, so we mark these with a 1. Then we move down and in. At each successive node, we add the number of paths from the previous nodes which lead to that node. So we move down and in, and there's 2 paths to that node. And then we get 3 paths to that node. Now we're moving across, and we get 1 from above, 3 from the left. So we get 4 possible paths, and then 5. And we continue this process until we've written the number of paths up to each node in each node. So we get 6, and then we get 10, and then we get 15. When we reach the final node, we know how many paths there are in total up to that node. In this case, there's 15 possible paths from home to work with no restrictions. In this example, we're still traveling from home to work. However, we're aware of a traffic hazard, which may be a crash or some roadworks at an intersection, and we need to avoid this intersection. We've extracted the network diagram again from our map. The process is very similar to when we found the number of paths. In this case, first we put a 0 in the node that we need to avoid. Then we follow the same process as the number of paths. We write a 0 in the home node. We then look to the next step in our journey. From the home node, there are 2 possible nodes we can move to, so we write a 1 in each of those. Again, there's only one possible path across the top and down the left, so we can write a 1 in all of those nodes. Then we move down and in, and we add the number of paths from the previous paths to that node. So we've got 1 from the top and 1 from the left is 2, and again we go 1 from the top, 2 from the left is 3. This time we've reached the node we need to avoid, and we revert. You'll notice we revert back to 0 for that node. So we skip over it. And then in the one in the middle on the right, this time there's only one possible path to that node, and that's from above because we had to avoid that intersection. Now we follow the same process along the bottom. There's 3 to that one. And now there's 6 possible paths to that. This time we're blocked from above, so there's only 6 paths along the bottom. And then we reach the final node. And this time there's 7 possible paths up to the final node with a restriction. In this example, imagine you need to pick something up on your way from home to work. In our example, we're going to pick up breakfast. So we must visit a specific intersection. Again, the process is very similar to the number of paths algorithm. There's one small difference. First, we start by putting a 0 in all of the nodes that we can't go to. If we went to these nodes, we wouldn't go to the node that we must visit. So we write a 0 in all of these nodes. Then we go back to the home node and we write a 0 in the home node, and we follow the same process we followed for the number of paths algorithm. So there's only 2 possible paths from the home node, so we write a 1 in each of those. And there's only one possible path across the top again, so we write a 1 in those nodes. This time we've gone as far as we can down the left because we've written a 0 in that bottom node. Again, we repeat the process. We move down and in, and we add all the paths from the previous nodes leading to that node. So there's 2, and then we get 3, and then we get 4. We've got 1 from above and 3 from the left at the node we must visit. And then we carry that across because we can go right, but this time we're blocked from above because we wouldn't have visited the node that we need to visit. So there's only 4, and there's 4 below. And this time there's 8 possible paths from home to work when we must visit a node to pick up our breakfast. In summary, in this video, we've looked at what the number of paths is, finding the number of paths with no restrictions, finding the number of paths with a restriction, and then finding the number of paths when we must visit a node. Thank you.